All right, so today we're going to start and hopefully finish section P.5, which is factoring polynomials. You guys watched a video on P4, which was about polynomials and characteristics and things like that. So we're actually going to specifically talk about factoring in this case to simplify expressions, and we'll be using more of this particular material when we get to, I think it's chapter 3 later on. So taking a look at this, when we're talking about factoring, if a polynomial cannot be factored, we say that the polynomial is prime or irreducible over the integers. When it comes to tests, quizzes, and things like that, I don't ask vocab questions. I don't ask matching. I don't do stuff like that. So anything that I'm giving you when I'm talking about definitions, it's so that when you see that asked in a question, you know what it's asking you. So if something says, is this prime, you need to know what it's asking. And that's the reason for talking about the language involved. So prime simply means it can't be factored. That's all it means. And that's the phrase we usually see listed as, or used as the word prime. So one of the ways, and in fact the first way that you should look at factoring is you should look for what's called a greatest common factor. Whether there's two terms like this one, so a term, as we talked about in section P4, means the pieces that are separated with addition and subtraction. There's two terms here. So whether there's two terms or whether there's 3 or 4 or whatever, greatest common factors means looking at everything you have in each individual term and seeing what they have in common. So let's start first with the coefficients, 12 and 18. What is the biggest number that goes into both of those? 6, exactly. So we're going to pull out a 6 in front. So that's the coefficient part. And then we look at the variable part. So this one has an x squared and an x cubed. So what's the biggest variable component that they have in common? X squared. So we're going to pull the x squared out as well. Okay, so those are the pieces that they have in common. But what we want is we want an expression that's equivalent to what we started with. So what I want to put inside the parentheses is what's left over when I divide each one of those pieces by 6x squared. So in the first one, it's 12x squared. So if I take 12x squared and I were dividing it by 6x squared, what's 12 divided by 6? 2. And then when I divide x squared by x squared, I get 1. It goes in evenly, so there's nothing additional that I get, right? It's not 0, but I don't get anything new. No more information, no more variables left. So it's simply 2. And then I do the same thing with the 18x cubed. So what's 18 divided by 6? 3. And then when I take x cubed and divide by the x squared, what do I have remaining? An x. I have an leftover x. So this would be factoring out a greatest common factor. So I'm not just identifying what is the greatest common factor. I mean, if the question asked that, we could do that. But I'm actually taking the greatest common factor out in front and then putting all the leftovers in the parentheses next to it. Does that make sense? Okay. There are some special formulas for factoring that you need to be aware of. I know you've seen them before. Again, I don't know when that would be, if it's been recent or a very long time ago. The first one, well, they all have names. The first one's name is called a difference, right, because it's subtraction. So I'll abbreviate. It's a difference of squares. It's difference, subtraction. It's each piece is squared. So if the first one's called a difference of squares, what do you think the next one might be called? Yep, it's a difference of cubes. And following the pattern, what do you think the third one might be called? It's not a difference, it's a sum. Yeah, so it's a sum of cubes. Notice there's no sum of squares. That doesn't exist, okay? So these are our 3 special formulas that we're talking about kind of grouped together because they all have a similar form. So these are the names. I'll just put them in sort of parentheses next to it to remind us. But they each have a way of factoring that's unique. So when I have a difference of squares, the way that it factors is a minus b, a plus b. Or if you want, you can put a plus b, a minus b. It doesn't matter. But you have the square root piece of each of the terms, right? So what's the square root of a squared? Well, a. What's the square root of b squared? B, right? And it's a difference, so I end up with one of them being a negative and one of them being a positive. So why does it work? Well, the reason it works is because if you were to multiply this back out, a times a is a squared, right? And the b and the negative b gives me negative b squared. Like, that's why you get the a squared and the b squared. You might ask yourself, well, but why am I not getting any middle terms? And the reason that you're not is because if you take a look at the middle of this, on the inside you get negative ab, and on the outside you get positive ab. When you add those together, they add to 0. So that's why there's only the a squared and the b squared left, okay? So that's what's happening when we factor that one out. The second one and the third one are very similar, difference of cubes and sum of cubes. Each of them have a component that looks much like what we did on the difference of squares. The first one is a minus b, that's the first component, and the second one has the first component is a plus b. So it kind of looks like, I'm not done with them, don't worry, but it kind of looks like what I just did on the other problem. I like to remember it because it matches the sign. So the one here that's going to have two terms, a and b, that much looks like this one, it matches the sign. So this is a negative from that negative, right? This one's a positive, just like this one had a positive. Now the other component of it is actually a trinomial. So the trinomial component of this is a squared. It's the opposite sign, so plus ab and plus b squared. Over here, I have a squared, and it's the opposite sign of what I had, so minus ab, and then plus b squared. So the signs switch. So if I have a binomial term that's subtraction, then the middle term here is addition. If this binomial term is addition, this middle term is subtraction, it's negative. Okay? And again, it's kind of like the squaring piece, right? I have the a squared, I have the b squared, right? That's what's giving me a squared times a is a cubed. And the middle term is the two multiplied together. It's the a and b multiplied together. Okay? It's a memorization thing, I get that. But these are the three. And they do have some nice patterning to help with the memorization, I think. So that's nice. So let's do a few examples that have this variety. So as we're looking at them, the first thing we have to do is to identify which of the three formulas it's asking me to use first. So on number 2, 9t squared minus 16. Which of those three does this look like? Yeah, the first one, it looks like a difference of squares. You have to be a little bit careful and ask yourself what's being squared. So on the back end, this is clearly 4 that's being squared, right? No problem there. But what about the 9t squared? What is it that's actually being squared? 3t, right? The 3 and the t are both squared. So it's not 9t. It's kind of a habit to look at and just forget about the coefficient part of it, but it matters, right? It's a different value. I need the 3 to be represented because the 3 and the t are both squared. It's nice sometimes to identify these two pieces because once I identify kind of what A is and what B is, I can apply that formula very directly. So back in that formula that we had on the previous slide, it says that I'm going to do A minus B. Well, A is 3t. And b is 4, so that's 3t minus 4. And then I'm going to do a plus b, so that's 3t plus 4. Any questions on that? So I didn't exactly ask the question on number 2. But I made comment of it back when we did number 1. Look back at problem number 1. What was problem number 1 asking us to do? Do you remember how we approached it?
Greatest common factor.
Yeah, we were looking for a greatest common factor, and I made the comment at that point that it's kind of the first thing you should do with any problems that you're looking at. The idea of whether there's 2 terms or 3 terms or a bunch of them or not, whatever. And we actually have that going on in this problem. So take a look here. I've got an 8 and I've got a 27. Those don't have anything in common. But what about the x to the 4th and the xy cubed? Yeah, I have to take out an x to start with. So the first step I'm going to do here is to pull out an x, leaving me with 8x cubed, like you just said, minus 27y cubed. You see, the problem before is that it didn't match any of the patterns of the special formulas I had, right? And there was an x to the fourth in it, for goodness sake. And I had variables that were being multiplied, an x and a y. Now, the same could be said to be true about numbers. I mean, we could have the coefficients themselves also have something in common that we factored out. These just didn't happen to have that, all right? So now taking a look at each of these pieces. What is it that's being, well, which of the three formulas that I have am I going to use now? Difference of squares, sum of cubes, or difference of cubes? Is the difference of cubes. So I need to figure out what in the world is being cubed. So I'll write it above them in this time. So what is it that's being cubed in each of these cases? What is it? A 2 and a 3, good. So the coefficients, the numbers themselves are 2 and 3. Does everybody see that okay? 2 cubed is 8, and 3 cubed is 27. So what about variable-wise? What's being cubed here? The x, right? The x is being cubed. And then right here, it's the y. So the values that are actually being cubed are 2x and 3y. That is not a very good looking y. Let's try that again. 2x and 3y. All right, so on this problem, I have the x in front. None of that's going to change. And then because it's a cubed problem, I'm going to have a binomial and a trinomial. The binomial takes each of the parts that I've written as what's being cubed, puts them right here, and it matches the sign subtraction. So I have 2x minus 3y. So far, so good? Okay. The trinomial is the harder part, especially when you have components that have coefficients and variables. So the part right here where it says 2x cubed, I need to know what is 2x squared. So what is 2x quantity squared? Well, x squared. And what's 2 squared? 4. So I get 4x squared. I'm going to jump to the end next, and we'll do the same thing with the y one. So I need to know 3y squared. So I need to know what is 3 squared? 9. And then y squared is y squared. So I have 9y squared. In the middle, I need the opposite sign. So the sign previously is subtraction. So my opposite will be addition. And then what goes right here, I'll need to shift it to give myself a little more space, but what goes right here is these individual terms multiplied. So what do you get when you multiply 2x and 3y? 6xy, exactly. And then, of course, it's plus the 9y squared at the end. So my middle term ends up being positive 6xy. Number 64. Not number 64. Number 4. Starts with a 64. Number 4. Any greatest common factors that I can factor out of this one? Nope, because part of it's a 1, right? That makes it easy to identify that I'm kind of not interested in going that route. It's cubed. I see something that's cubed there, right? And it's a sum, because I've got addition. So this is a sum of cubes. But what in the world is being cubed? Well, let's take a look at the 64 part first. There's a z in there. What number cubed is 64? 4. It's 4, that's right. We don't always know our cubes as well as we know our squareds, but that's okay. It's 4. 1 feels funny to be doing here, but it's okay. What number cubed is 1? 1. So I really have 1 cubed here. It's not very exciting to cube a 1, but that's okay. We can do it. All right, so when I factor this, again, I've got a binomial term and I've got a trinomial term. The binomial takes each of the pieces that I have, in this case 4z and 1, and the sign will match, which means the sign is a plus, right? It's addition, because the sign in the 64z cubed plus 1 is addition. On the other piece, in the first spot and in the third spot, I'm squaring things. So the first one, I need my 4z, and I need to square it. So what is 4z squared? Yep, it's 16z squared, right? Because I square each part. Square the 4, square the z. At the end, I need to square my 1, which is the super exciting number of 1, right? It is, yeah. And then in the middle, I need each of these pieces, A and B, what is being cubed, right, multiplied together. So what do I get when I multiply 4z and 1? I get 4z. And I need to do that with the opposite sign, which means the sign here will be subtraction or negative, right? And then I'm done. Now here's something I didn't think to mention before, but I think I probably should, because we will see that it doesn't always work that way. When we have these particular types of problems, in particular the difference of cubes and the sums of cubes, and we have this trinomial piece, the trinomial piece will never factor any further. This piece itself is prime. Okay? So we don't have to get to this point and say, okay, but does this piece factor? It won't, because it was a sum of cubes or a difference of cubes to start with. Okay? It will not go any further. So that's kind of nice to know that at that point you're finished. Any questions on those? Okay. The next thing we're going to take a look at is something called factoring by grouping. Factoring by grouping typically looks like we have 4 terms in it. I'm going to show you a variation where it doesn't have that feature, but we're going to start out with the 4-termed feature. So it looks like there's 4 terms, and what we want to do is we want to find a grouping where I can factor things out. And we may not choose the right grouping at first, and it's okay. We will know if we've gotten it right. I'll show you how we know. And if we don't get it right the first time, we just scrap that and we try a second time, okay? And we'll get it right the second time because there's usually only a couple of options that actually are plausible, okay? So when we're looking at factoring by grouping, it's natural to just try where they are to start with. In other words, to sort of group these 2 together and to group these 2 together. Okay, they're already there. We might as well try it in the order it's already in. So what we're doing when we look at this is the first 2 terms, 2w cubed and 2w squared, is we're looking to see what's their greatest common factor. So what is the greatest common factor for the first 2 terms? Wonderful, it's 2w squared. So we're going to write 2w squared. And just like the first problem we did today, then we're going to write the leftover pieces in between. So if I take 2w cubed and I take out a 2w squared, or divide by a 2w squared, what do I have left? W. And if I take negative 2w squared and I divide by 2w squared, I have left 1. And it's a negative 1 because the sign was negative, right? When you divide something by itself, it's 1. So you're always going to have something left there. It's never going to be 0. We're going to do the same thing with the second grouping. 3w minus 3. What do they have in common?
3.
A 3. And it's a positive, so I'm going to write positive 3. And we're going to do the same thing. 3w divided by 3 is w. And negative 3 divided by 3 is negative 1. Here's how we know if it was the right grouping. And there is wrong groupings, okay? Here's how we know that it will work, that we have a good or a right grouping, is that the parts that remain in parentheses right now match. That's our goal when we're factor by grouping, is that the parentheses parts match. If they don't, then it means that you need to go back and try the different grouping. And so maybe instead of doing the first 2 terms and the last 2 terms, you do the first term and the third term, and the second term and the last term.
You can group whatever you want.
You can, but they don't all work. But you can group whatever you want to see if it will work. So if this grouping didn't work, we'd have to try something else. And there's really only 2 other options. The other 2 options are to either go with the first and third and second and fourth, or the first and the last and the middle two. First and last and middle two seldom work. I'm not going to say never, but it's usually not the best choice to go with. Okay, we're not finished yet, but we know we've got a good grouping, right? We've grouped them well because those parts that I've highlighted in yellow match. So now think about this. Our whole idea is to pair things up and to move things around so that things match. So let me use this. That's not a great color, but it'll work okay for now. If I take everything that I've sort of underlined here in this funny yellow color, and everything that I've underlined here in the funny yellow color, what matches? The W minus 1, which was what I said was our goal, right? The part in parentheses matched. So what we're literally going to do is we're going to factor out the part that matches, the W minus 1. So when I pull the part in parentheses out, so taking everything that's been underlined here in yellow, and if I pull out the W minus 1, what am I left with? 2W squared. Whoops, that's not a very good 2. And if I take everything that I've underlined in yellow in the second piece, and I take out the W minus 1, I'm left with the plus 3. I'm not going to go through the step to do this, but let me let you know. These problems are one of those variety of problems that are very nice because you can always make sure you got it right. If you wanted to make sure you have it right, you multiply it all back out. And it should match where you started. And if it doesn't, then there's a mistake somewhere, either in your multiplying it back out or in your original factoring. All right, let's give give number 6 a try. Taking a look at number 6. If I try to do the same thing and group them where they are, what do you notice? Seeing shaking of heads. There's what? There's nothing in common, right? Each of the pairs that I've grouped together don't have anything that factors out. That's a red flag that this is not a good grouping. It's not the only way that the grouping can end up not being nice, but this definitely qualifies. So I need to shift something around and make it different. For the sake of making it, easier to see, I'm going to put these two together. So I'm just going to rewrite it so I can see it better. ADY plus D. And then I'll do the middle, like the second and the fourth one together. So I have minus W and minus AWY. Okay, so again, it's not the only thing I could try, but it's a possibility to try. We can see if it works. And if it doesn't, we'll try something different. So on this one then, looking at those first two after I've rewritten them, what do they have in common? D. And if I take out the D, what am I left with? AY. And what else? Yeah, plus 1. Okay, what about the second one? Well, they've got a negative in common, right? They do. What else do they have in common? A W. And if I take out the negative W, so if I do, right, this is negative W divided by negative W, I get a 1. And if I have the negative AWY divided by negative W, I get a positive, what? AY. So what we want to do is we want to look at what's in parentheses and ask ourselves, do they match? And they do. They're in a different order, right? But just like 5 plus 2 is the same as 2 plus 5, that's okay. They're exactly the same, right? It's okay. So we're going to do the same thing we did on the last problem. We're going to take a look then at all of this and all of this and say, what do they have in common? We know it's the part in parentheses, written either AY plus 1 or 1 plus AY, it doesn't matter. And we're going to ask ourselves what remains. So if I take D times AY plus 1 and I take out the AY plus 1, what am I left with? Just the D. And then if I take the negative W times 1 plus AY and I take out the 1 plus AY, I'm left with minus W. Okay. Interestingly enough, just so that you know, in my notes, I actually grouped the middle two together and the last two together on this particular one. And that grouping works as well. It's another way of grouping, and it would have worked equally well. It works out a little bit differently in the intermediate steps, but you get the same answer at the end. All right, we are going to look at 3 terms next. I don't think we'll quite get finished with this lesson, but that's okay. We'll chat about that at the end. First, we'll need to write down what's going on here. There's lots of ways. I can think of at least 3 different ways of factoring trinomials, 3 terms. So I'd like to show you one way. If you don't like my way of doing it and you want to do it a different way, I'm okay with that. It's not going to hurt my feelings at all, I promise. But this is one option. This is called the AC method. In the AC method, you take a trinomial, like ax squared plus bx plus c. And what you do is you multiply the integers a and c together. So the first, the squared term's coefficient, and the constant term at the end. So you get a product of that. And you look at the middle term, its coefficient, the b. And what you want is you want 2 integers whose product is AC and whose sum is b. You replace the b by the sum of these 2 numbers, and then factor by grouping. There's pros and cons to every strategy for factoring, I think. The con to this one is it's not terribly efficient. Efficient means fast, right? It's super effective, which means it always works. So sometimes you got to get a little give and take. Another method, and you can do it this way too, if slide and divide. If you know slide and divide and you want to use that, the Success Center students will sometimes show you methods like that. That's fine. It's not a method that I ever teach because I feel like that what's really going on is very hidden. You can't really see why it works. A third method, and the method that I learned and is most comfortable and natural to me, is simply trial and error. Okay. Good news is if you try it and it's right the first time, super efficient. If you don't try it, or if you try it and it's wrong, you might try several things before you ever hit on the right one. So it can be also inefficient depending on what you're working with. So it kind of depends on the terms. Let me show you actually how this one works, okay, with AC method, because you've got all the details written down. So what we're going to do is kind of on to the side, I'm going to write down what is A times C and what is B. So on this one, it's really nice. I've chosen something that's super clean that would be super easy to do with trial and error, by the way. I get that. So this is not a very good, like, see, I told you how great it was kind of example. That's not what this is. It's very simple on purpose. So what we're going to do is we're going to multiply A times C. So A is the coefficient in front of the square term, and you see that that would be a 1, right? And the C is 12. So A times C is 1 times 12, which is 12. And B is your middle coefficient, which is 7. So that's you have to identify what is AC and what is B for this to work. And then what you're wanting to do is you're wanting to find 2 numbers that multiply to 12 and add to 7. What are those numbers? 4 and 3. So 4 times 3 is 12. 4 plus 3 is 7. 4 and 3 are the numbers I want. Everybody agree? Okay. So before you jump the gun and think you know where you're headed next, slow down and let me show you where it happens, because on this one it's easy to mistake what's happening next. What you're doing is you're going to take the 7x in the middle and you're going to rewrite it in whichever order, it doesn't matter, as 4x plus 3x. Or you can do 3x plus 4x. So the AAC method has you take the middle term and break it apart. And in particular, you're breaking it apart into 2 pieces that add to the middle term you already had. That's what you're doing. And then we're going to factor by grouping. And the beautiful thing is when we factor by grouping here, the groupings, they always work. So you never have to worry, like, is it going to work out? It will. Or you've made an error accidentally and it's time to figure out what the error is. So taking a look at the first 2, x squared and 4x, what do they have in common? An x. And if I factor the x out from x squared, I have x. And from 4x, I have 4. 3x and 12, what do they have in common? 3. So if I factor 3 out of 3x, I have x, and from 12 I have 4. And lo and behold, as predicted, these match. Okay? So again, like what we're doing with factoring by grouping, when I consider each of the components right now, they have an x plus 4 that matches. And if I take the x plus 4 out of the first piece, I'm left with x. And if I take the plus 3 of the second piece, I'm left with 3. Caution. Yes, I realize that 4 and that 3 are the 4 and 3 from here. The reason that happened was because the coefficient here was a 1. If this coefficient had not been a 1, these numbers down here would not match the numbers that we worked out okay over here. Okay, so be aware of that. All right, so here's the deal. We're obviously not finished with P5. That's okay. So what I'm going to do is I will go into my math lab. I will adjust the due date. This will not be due on Wednesday. It will be due on Friday. But we will finish this one and hopefully finish P6 on Wednesday. So if you want to avoid having to do 2 lessons between Wednesday and Friday, I would suggest going ahead and starting this one and going as far as you're able to. Pause when you're not, and you're paused for the day. Okay? Have a great week, and I will see you guys on Wednesday.